How we doing today? Uncle Lee here with you with a little discussion on how to find the volume of solids. What I'd like to end up with today is to specifically find the volumes of solids whose base is bounded by some area, and cross-sections of this solid are going to be squares, rectangles, or triangles. But I'd like to begin by reviewing what kind of solids that we find the volume of. And this is one of the major applications of integration, is to find the volume of solids. And there are going to be two basic types of solids that we find the volume of. And these are solids that we could not use basic geometry to find the volume of. This is why we use calculus, one of the important applications of calculus. Well, the two basic types of solids that we're going to find the volumes of using calculus is the volume of the solids created when we revolve some bounded area around some horizontal or vertical line. This we have done on a previous video. This you should have looked at before. This is something that 10 years ago on the AP test, almost all of the problems were about revolving some area and finding the volume of that solid after you've revolved some area. In the past few years, you've seen more and more on the AP test, more and more volumes that are created when you have the base of the solid in some bounded area and the cross sections perpendicular to the x and or y axes. The x or y axes are squares, rectangles, or triangles. So these are the two basic types of volumes that we're going to use calculus to find the volume of. And we're going to begin by reviewing something that we have done in the past. Well, in either case, in either one of these cases, be it a volume that was created by revolving something, and this is where a lot of us forgot about when we were revolving this area. When you revolve something, or when you have something bounded by the base, bounded by some area, and cross sections are perpendicular, either formula is this. The volume is simply equal to the area of a cross-section from A to B dx. It's just the area of a cross-section. But if you're revolving something, a cross-section is either going to be a circle or an analysis. This is something we discovered previously. It could be the area of a cross-section with respect to if the area of the cross-section is perpendicular to the y-axis, then I'm simply going to have an integrand in terms of y, and I'm going to integrate with respect to y. If this were the case, then these a and b's, the limits of my integration would be y values. To make things simple for today, we are going to make sure all of our cross sections are perpendicular to the x. So we're going to limit ourselves right here. Okay? So, example number one. In example number one, I'm going to review taking an area and revolving it around, taking some bounded area and revolving it around some horizontal line. So what I'm going to do is consider the area bounded by the graphs of x equals 0, the constant function f of x is equal to 2, and our old friend, the square root function, g of x is equal to the square root x. So this is the area that I'm talking about, the yellow area there. I have x is equal to 0, y is equal to 2, and square root of x. And this is that bounded area. And I'd like to begin by finding the volume of the solid created when I revolve this area around the line y equals 2. So this is what I'm going to be doing. I'm going to revolve that area around the line y equals 2. And if you recall, the first thing I do is go to the axis of revolution, which in this case is going to be y equals 2, and I determine if there's going to be a gap. In this case, there is no gap. If there is no gap, then the cross-section of this creature is simply going to be a circle. If there is no gap between the area and the axes of revolution, the cross-section is a circle. And the area of a daggone circle is pi r squared. Simple. And I'm going to integrate this from 0. This point of intersection right here is going to be 4, 2. And since the cross-sections are perpendicular to the x-axis, I'm going to integrate with respect to x. And the limits of integration are going to be x values. In fact, we're going to go from 0 up to 4. So the volume, very simply, is going to be, well, I need to find r. Well, what the heck is r? R is this distance right here. R is that distance. And what is vertical distance? If we remember, vertical distance is always top minus daggum bottom. Top, take away bottom, that's the vertical distance. And in this case, that's going to be our r, because we're studying the center of rotation. So the vertical distance is going to be top, which is 2, minus the bottom, which is square root of x, so this is r. So therefore, my volume, very simply, is going to be the integral from 0 to 4, the area of a cross-section. What is the area of a cross-section? Pi r squared. Pi r squared. The volume, pi r squared from 0 to 4. Cross-section circle. Think about cross-section, perpendicular to the x. Next example. If you need to pause the video. Or fast forward it. I want to look at the same bounded area this time, and this time I want to revolve. I want to look at the same bounded area, revolved around the line y equals -1. Still a horizontal line. The horizontal line that is below the x-axis. I'm going to revolve this around y equals -1. Revolving around that guy right there. And this is the area that I'm going to revolve. And if I think about this, we did some of these with Play-Doh. What's a cross-section look like? Well, now there's a gap. There's a gap between the area and the axis of revolution. So the cross-section is an annulus. The area bounded by 2 concentric circles. The annulus. And the area of an annulus, pi big R squared minus pi little r squared. Keep in mind, take a deep breath, this is a review. We've done this before, if I'm not mistaken. I have another Uncle Lee video about volumes of revolution. Here there's a gap. Pi big R squared, pi minus pi little r squared. What I need to do, I need to find these vertical distances. This is big R. You start at your center of revolution, you go to the farthest portion of the region, that's going to be big R. In this case, vertical distance is always top minus daggum bottom, always top minus daggum bottom. So this time, R, big R, is going to be 2 minus -1, which is the bottom. That's the vertical distance. 2 minus -1. Little r, which is this distance, or this distance, or this distance. Little r, the square root of x, minus the daggum bottom, which is square root of x minus -1. Big R, little r. Cross-section, annulus. Cross-section, pi big R squared minus pi little r squared. So therefore the volume is going to be the integral from 0 to 4, and I'm factoring, keep in mind, I'm factoring the pi out of the big R squared, and I factor the pi out of little r squared. This is big R. Keep in mind I have parentheses, big R squared minus little r squared. Square root of x minus -1, that thing squared, this thing squared. This would get you all of the points on the AP test. So the volume of this particular solid is pi, integral from 0 to 5, 0 to 4, big R squared minus little r squared. That, my friends, is a review. Volumes of revolution. Now, what if I have this creature right here? I want to look at the area bounded by x equals 0, the exponential function e to the negative x plus 2, and this linear function, negative 2/3 x plus 5. And what I want to do this time, I want to think of the volume, I want to think of the solid whose base is bounded by this area, but whose cross sections perpendicular to the x-axis are squares. Squares perpendicular to the x-axis. The base is bounded by this area. And cross sections perpendicular to the x-axis are squares. What I'd like to do is I have a little manipulative over here, and I want to show you what I'm talking about. This is hard. This is tremendously hard to envision what it looks like. So I have the same graph here. Are we good? All right. We have the same graph here. We have the exponential, e to the negative x plus 2, and I have the linear equation. And what I have here this time, cross sections perpendicular, the base of the solid is going to be bounded by this area. But cross sections perpendicular to the x are squares. And this is a square. And this happens to be a square whose base is bounded by that area. And if you notice, this square is perpendicular. If I slide the square down here, it's perpendicular to the x-axis. If I went with this way, those are not perpendicular to the x-axis. That's parallel to the x-axis. The question might ask, perpendicular to the y. Well, this will be a different problem. Here, my cross-sections are squares perpendicular to the x-axis. Well, that's what it would look like. Well, that's what one cross-section, one square would look like. What would the whole solid look like? Well, the whole solid would look like this creature. Really hard to envision. And you might maybe zoom in on this creature right there. So that's what the whole thing would look like. Can you zoom in on that? So all of these cross sections are squares, and if you look, if you get down here, they're going to be little itty bitty 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 squares. The biggest squares would be right here on the end. But each time, those squares are perpendicular to the x-axis. Well, to find the volume of that, it's so easy. It is so easy. So what I'd like to do is come back over here to the active inspire. Keep in mind that manipulative, what it looks like. Okay. Find the volume of the solid whose base bounded by the area and whose cross-sections perpendicular to the x-axis are squares. Went to the manipulative. So, I'm going to make a note here. These graphs, I had to use this was a calculator active problem. These graphs intersect at the point right here. At this point right here. This point is 4.4830517. Keep in mind, we don't round to the very end. Leave big long decimals till the very end. Cross sections are squares. Well, here the cross sections is a square. What the heck is the area of a square? Here's what the area of a square is not. The area of a square is not pi s squared. You have no idea how many people, how many calculus students make this mistake. The area of a square is not pi s squared. The area of a diagonal squared is s squared. So all I need to do is find s. What is s? What's s? Here's s. Here's s. Right here. S is a vertical distance. Don't make this difficult. This is the easiest stuff that you've done. S is a vertical distance. What is s? Well, here's the volume. The volume is simply going to be the integral from 0 to that 4.4830517 s squared dx. So all we need to do is to find s. Find s. What's s? S is a vertical distance. S is the top minus the dadgum bottom. Top minus dadgum bottom. What's the top? The top is that linear function. The bottom is that exponential. Top minus dadgum bottom. That's s. So what's the volume? The volume is simply the integral from 0 to 4.4830517 of S, which is top minus bottom squared, S squared. So that's the volume. That is the volume of this guy. Who'd have thought that we could find the volume of that? Well, obviously Newton did. Too easy. Too easy. Well, what if I want to change it up a little bit? What if I want to really make it difficult? Then I say, hey, I want to find the volume of the solid whose base is bounded by the same area and whose cross-sections perpendicular to the x-axis are rectangles with a height of 5. What's the area of a daggone rectangle? Well, that's hard. Base times height. Well, the height is 5. What's the base? The base is going to be this. Now we have a rectangle. Base, height to 5. Base, height is 5. The cross-section is a rectangle. The area of the rectangle is 5 times the base. 5s. 5s. The area of a rectangle isn't pi base times height. It's just base height, or height base. So what is the volume? The volume simply is going to be the integral from 0 to that 4.4830517 of 5 times s. 5 times the base. The base being that vertical distance. Top minus daggum bottom, 5. I guarantee you, ladies and gentlemen, boys and girls, that on your AP test this year, for the last 5 years, they've been really, really, really going back to this original definition of a volume. The volume of anything is simply the integral from A to B of the area of a cross-section. If you're revolving it, it's going to be a circle, pi r squared. If there's a gap between the axis of rotation and the area, it's going to be a manifest, pi r squared minus pi big R squared minus pi little r squared. Or there are going to be some easier problems, which traditionally are difficult for calculus students. Cross sections are squares. S squared. Rectangles. Height times the base. There was a few years ago a very clever problem. Find the volume of a pond. And they gave you the height of the pond was another function of x. Again, a very easy problem if you just remember the area of a cross-section. The volume is the integral from A to B, area of a daggone cross-section. Please do not make this difficult. Thank you.